Here we are in exercise 4 of chapter 13. This exercise is going to introduce you to some of the many wacky and interesting properties of random matrices. There are entire mathematical theories that are built around the properties of random matrices. In fact, one of those properties I use throughout this book, which is that a random numbers matrix is going to have, almost guaranteed, to have a full rank, to have its maximum possible rank. Okay, and here is another interesting property of random matrices. They tend to have complex valued eigenvalues, not guaranteed. You will also get random numbers matrices that have real valued eigenvalues, but many random numbers matrices have complex valued eigenvalues that are distributed in a circle on the complex plane with a radius proportional to the size of the matrix. What a weird thing. Okay, we can visualize this. So here we have, let me zoom out a little bit. Here we have a complex plane. So we have a real axis and the imaginary axis. And each dot in here corresponds to the eigenvalue of a particular random numbers matrix. And you can see that the radius is basically 1. And that's because I scaled the eigenvalues according to the square root of the number of rows. I'll talk about that in a moment. If you look at this, you see that there actually is a flat line over here, and that corresponds to the eigenvalues that have a 0 imaginary component. So that means that there are a bunch of random matrices that we created purely by chance, right? It's just random matrices, random numbers that are not complex valued. They are real valued, and so they don't have an imaginary part. You can also see, if you look more carefully, that it looks like this circle is mirrored. It looks like it's reflected across the imaginary axis. So, for example, here's this point here and this point here. And I don't know, this cluster here mirrors this cluster here, this point here, and this point here, and so on. In fact, when a matrix has complex valued eigenvalues, they are complex conjugates of each other. So that means that this would be eigenvalue 1, and eigenvalue 2 would have exactly the same real part, but the imaginary part is the same magnitude, but it's sign flipped. Pretty wacky feature about complex matrices. So here's what you want to do to create this plot. Compute 42 by 42 matrices, 123 of them, extract their eigenvalues. You don't have to worry about the eigenvectors. We don't need that here. And then use scale or divide by the square root of the matrix size, so the number of rows or the number of columns. Okay, and then you just plot the eigenvalues on this complex plane here. So now I will switch to Python and I'll show you. It's mostly straightforward code. There's a couple of little tricks that you need to keep in mind. I guess the only tricky thing about this code is that when you initialize the matrix of eigenvalues here, you need to explicitly define that this matrix can accept complex valued numbers or can represent complex valued numbers. If you ignore this, then you are not going to get the correct result because here you see this warning message, casting complex values to real matrices discards the imaginary parts, and then we just get a line. And so basically what's happening here is all the imaginary parts have been removed. They've just been truncated, and that's because of this issue with the data type here. So you say d type equals complex, and that will allow us to store the complex valued results, and you get this plot that looks like this.